This is the first of 8 video lectures introducing you to nodal analysis and mesh analysis, 2 circuit analysis techniques that will allow you to solve for unknown currents and voltages in a linear circuit. And the techniques will be developed by way of solving some circuit examples, each example kind of building on the previous one, adding a new feature in the circuit and thereby some complexity in the analysis. Before you watch any of these examples, you should watch a preliminary video called Get Smart, an overview of network analysis, which kind of lays the groundwork for nodal and mesh analysis. So I'd recommend that you go to view that, especially if you start watching me solve these and you're wondering, why are you only solving for these voltages or these currents? That introductory lecture should help answer those questions. So the first couple examples here are going to be working with, I think, or at least the first example is nodal analysis. So we'll start with that one. And this is the simplest type of circuit we could solve because it only involves resistors and current sources. We'll later see what happens when we add voltage sources into circuits that are solved by nodal analysis. So recall that with nodal analysis, what we're going to be doing is solving for unknown node voltages. Now you know already that when we define a node voltage, it's only with respect to another node voltage. So here, this circuit has three nodes. Okay, there's a ground node, or what I'm going to term a ground node. I'm going to choose this lower node as my reference. It doesn't have to be, but that's the one I'm choosing. We have this node at the top left and then another node at the top right. We have 3 nodes, but we will solve for 2 unknown node voltages. So in other words, we always solve for n minus 1, solve for n minus 1 node voltages. Okay, because one of those nodes has to be set, that has to be used as the reference node. So we're going to write n minus 1 equations, okay, having n minus 1 unknowns. So in this case, n is 3, right? So we're going to write 2 equations, and our 2 unknowns are V1 and V2, the voltages associated with these 2 nodes. Okay. So how do we go about doing that? We're going to write a Kcl equation, Kcl, at each of those nodes. So we're going to write Kcl at node 1, and we're going to write a Kcl equation at node 2. So I'll take kind of baby steps this time, or at least this first time. I'll label some currents. I'll call that I2, and I'll call this current here I5. Okay, and let's write a Kcl equation at node 1, and I'm going to sum currents leaving. So I'm going to sum I leaving. That's my note. That's my convention. You can choose currents entering. So we have minus 3 amps leaving, right? Because we got 3 amps actually entering. So I've got minus 3 amps leaving. And then I've got I2 leaving through the 2 ohm resistor, and I have I5 leaving through the 5 ohm resistor. Now the next thing we want to do is we want to replace all of those currents, in this case I2 and I5, with expressions that involve our unknown node voltages. And here's how that works. I2 can be expressed in terms of the voltage across the 2 ohm resistor, right? That voltage is just V1 minus 0, and we can get the current if we just divide that by 2 ohms. Okay, then we'll do the same for I5. The current I5 is going from left to right, and so we use Ohm's law and say that V1 minus V2, that's the voltage from left to right, divided by 5 ohms is equal to I5. And so now we have an equation that's in terms of just our unknown voltages. Let me clean that up. I'll put the 3 amps on the other side. And we will have 1/2 V1. And I'll actually collect these together. We'll say 1/2 V1 plus 1/5 V1 minus 1/5 V2. And this is our first equation. Okay, now we got to do the same thing at node 2. Now in this case, I'm not going to label the currents. We'll just try to do it directly. All right, so I have minus 2 amps leaving through my current source on the right. I have the current going down through the 1 ohm is going to be V2 minus 0 over 1 ohm. And the current leaving node 2 from the right flowing left is going to be V2 minus V1 over 5 ohms. Notice that's the opposite from what we had before, right? And that makes sense because in the one case we were talking about current flowing to the right away from node 1. Now we're talking about current flowing to the left away from node 2. Okay, and that is going to be equal to 0. We can again collect the terms. So here we'll have minus 1/5 V1, and then we have 1/1 plus 1/5 times V2, and that is our second equation. Okay, and now we just have to run some math. I'm not even going to do the algebra here. We have, this is equation number 1, and we have equation 2. So we have 2 equations, and we have 2 unknowns, V1 and V2. And you just use some algebra to solve those. Now, lastly, before we move on, I'm going to put this into a matrix form, okay? So in matrix form, in the general form here that we have is, if you notice, we've got over on the right, we have currently. And on the left, we have basically some conductivity. So you notice this 1/2. So this is actually 1/2, 1 over 2 ohms, 1 over 5 ohm, 1 over 5 ohms, 1 over 1 ohm, 1 over 5 ohms, right? So the reciprocal of 2 ohms is a conductivity. Remember, we use G for conductivity. So I'm going to write this in a matrix form saying G, this matrix G, times a vector V. And so I'll put a vector like that, and I'll say this is equal to a current I, and that's a vector as well. Now let me kind of flesh this out so you can see what I'm doing. I'm going to just take those 2 equations and I'm going to put them in a matrix form. And we're not going to solve them right now. I just want you to start practicing putting them in the standard form because it's quite efficient. So I'm going to put V1 and V2 here. And if you recall, when you multiply, if I have A, B, C, and D in this matrix, when you multiply a 2 by 2, that means 2 rows by 2 columns, and you multiply that by a 2 rows by 1 column, okay, you end up with the overall size is the outer dimensions here. You'll end up with a 2 by 1, which is a good thing because that's what we have over here, a 2 by 1. And the way you multiply it is you take A, you multiply it times V1. So let me go ahead and write this out. We'll have A times V1 plus B times V2. Okay, and we'll do the same thing on the bottom. We'll do C times V1 and D times V2. Okay, that's this right here, and then the whole thing is going to be equal to these currents, which will be 3 amps and 2 amps. Okay, well, if you look at this form here and you look at this equation here, they have the same form, right? We just need to replace A and B with the coefficients that are out in front of V1 and V2 in our equation right here and right here, right? Let me clean all this off. Okay, and let's go down and rewrite this as a final step, okay? So what we'll have is A is going to be 1/2 plus 1/5. B is going to be minus 1/5. C is going to be minus 1/5. So here, they're coming from here, from here, from here, and then, oops, not that one. Here, and then lastly from here. Okay. Oops. That's going to be times V1, V2 vector, and all of that is going to be equal to 3 amps and 2 amps. And this is what we call our matrix form for our system of equations. This is going to be the matrix G, a conductivity matrix, and this is our voltage vector, and here we have a current vector, or really we'll say in general a source vector. Okay, we'll call this source, because we'll see later that we can have other things besides current sources, although the units will always be amps over there. So I'm going to put a box around here, because if you had a problem that asked you write a set of equations in terms of the unknown node voltages V1 and V2, this would be your solution. Now if you were asked then to solve for V1 and V2, now there's a number of different mathematical techniques and tools you can use to solve that. So the one certainly that you can apply is you can use, if you have a programmable calculator that does matrix math, you can solve this. Right, and if you recall from some high school linear algebra maybe, or matrix math, if you have a matrix G times a vector V equal to another vector S, you can't divide matrices, but you can take the inverse of a matrix. And so you can multiply both sides by the inverse of G. And G inverse times G gives you the identity matrix, which is just, like in this case, it's a 2 by 2, so it just has 1s on the diagonals and 0s everywhere else. It's basically the analog to the scalar 1 for scalar math. And so what we have is that the voltage V is equal to, and we can just get rid of that now, that the unknown voltage vector V is equal to the inverse of our conductivity matrix times our source vector. So if you have a calculator or a computer program that can take the inverse of a matrix and then multiply it by a vector, then you could solve for this. Now in this case it's not necessary, because it's two unknowns. You could just do substitution and solve for V1 and V2 as well. But I thought I would give you a little intro to that, because a lot of the oftentimes when you're asked to set up the equations for a problem like this, which is where really most of the work is, you'll be asked to put it in matrix form at the end, and this is how you do it.